have three different types of apples: a light crabapple, a medium Macintosh, and a heavy Granny Smith. Although they're all apples, they differ in mass. This is basically what isotopes are. Isotopes are two or more forms of the same element that contain equal numbers of protons and electrons, but differ in the number of neutrons. Since neutrons are one atomic mass unit, taking away or adding them changes the atom's weight. Now have a look at these apples. We can count them pretty easily. There are 10 of them in total: 1 crabapple, 5 Macintosh, and 4 Granny Smith. Therefore, we have 10% crabapple, 50% Macintosh, and 40% Granny Smith. However, when it comes to atoms, it's a bit of a different story, since they're much smaller and harder to count. But, thanks to a few genius scientists like Thomson, Aston, and Dempster, a way to determine the relative abundance of the isotopes of an element was developed: the mass spectrometer. So how does this thing work? Well, there are 5 steps. The first step is vaporization. A bunch of heat is added to the sample so that all the atoms become gaseous. This is necessary for the next step: ionization. The atoms are bombarded with high-energy electrons, often shot from an electron gun, which knocks an electron from the atoms. Now they're all cations. Since the atoms are gaseous, their electrons are loosely held, making the ionization process easier. After ionization, the atoms must be accelerated. This is done by passing them through holes in 2 metal parallel plates that have a positive charge. Since the atoms are cations, they are repelled by the identical charge and zoom through. It's important that all this is happening under a high vacuum, so that air molecules do not interfere with the path of the ions. A magnetic field is now applied to the accelerating atoms, here. This is where they get deflected. Lighter ions will be deflected more, whereas heavier ions will be deflected less. To portray this, let's say that we have a small, lightweight ball, a tennis ball, and a baseball, each representing a different isotope with a different mass. When applying an equal force to all of them, like from a hairdryer, the lightest ball, which has a much lighter mass, will be deflected more by the hairdryer than the tennis ball and the baseball. A similar scenario is observed with ions in a mass spectrometer. It's a good thing it was made sure that all the atoms were cations back at the ionization station, or else their charge would affect the deflection as well. And finally, the last step to the mass spectrometer is detection. For a given magnetic field, only ions of a certain mass will reach the detector. All the others will be deflected into the walls. So, the strength of the magnetic field is adjusted until all the ions have reached the detector. As the ions of a specific rate reach the end of the mass spectrometer, they collect in a metal box. Here, an electric current is applied to determine the number of the ions that have reached the box. All this is then displayed digitally as a graph that looks like this. So, to recap, the process of a mass spectrometer follows 5 simple steps: vaporization, ionization, acceleration, deflection, and detection. You can remember this with the acronym VAD. Volcanoes in Australia don't detonate. Now let's move on to types of radiation. A radioisotope, also known as a radioactive isotope, is an isotope with an unstable nucleus. In an attempt to become more stable, they decay, releasing excess energy in the form of radiation. There are 3 types of radiation: alpha, beta, and gamma. Alpha radiation is the emission of alpha rays, which consist of 2 protons and a neutron. These rays are released during radioactive decay of an element. Alpha rays are the weakest of the 3 forms of radiation, unable to even pass through tissue. However, alpha rays can be fatal. Alexander Litvinenko was poisoned by polonium-210, an alpha particle which was placed in his tea. Beta radiation is the emission of beta rays, which are composed of high-energy electrons. These rays are produced when a neutron becomes a proton, after getting rid of a negative particle. They can travel through a few centimeters of skin, but do not cause much external damage. So far, the most damage beta and alpha rays can cause is internal, if ingested, for example. Gamma radiation has the shortest wavelength of the 3, emitting the strongest energy. Upon decay, a high-energy electromagnetic photon is emitted from the nucleus. Due to its strength, gamma rays are very penetrating and are able to pass through concrete walls. Lead, however, blocks gamma rays.
Just keep on recording till like get this right.
Oh, so close. So close.
It's the second one.